James. Okay. Thanks everybody for sticking around. I'm going to tell you about something today that most of you, but not all of you, have never heard about before. And so you have to bear with me a little bit. I'm going to have to give you an introduction, but I'm going to tell you about a way, probably the only way, to get at the bulk chemical composition of solid and rocky planets around other stars. And it's using a technique that I like to call archaeology because it involves stars that represent the future state of our sun. And I hope to convince you today that it's a powerful technique and most likely the only game in town. All right, I have to thank many of my collaborators, most of which are in this room. And this technique, which I will slowly tell you about, has at least two, but a few unique points on what it can achieve empirically. One thing that the technique can do that other things can do is it can tell us the frequency of terrestrial planet construction. Kepler can do that too, but this is an independent method. What this technique can do is it gives us this bulk chemistry of large planetesimals, the building blocks of rocky planets. We can get mass constraints for these planetesimals. And one of the sub-aspects of this is that we can actually get the frequency of water-rich rocky planetesimals, which are important for delivering water and volatiles to Earth-like planets around other stars. Okay, so why would we want to do this thing? Well, I hope it's a pretty obvious kind of interesting question to everybody in this room. What are other solid planets made of? We've heard a few talks about that today. We only really have models and densities, and I think this is kind of well represented on this plot, which is a little bit old. I hope the Kepler folks will forgive me for using this plot, but it's nice because even 1 year ago, or a little bit more than 1 year ago, we had plenty of Earth-sized planets. But we have here Mr. Pink and Mrs. Blue and Mr. Red and Mr. Green. It's just we just don't know what they're made of, and Kepler can't tell us what they're made of at any detailed chemical level. And I think everybody kind of knows this, but it's worth just kind of looking here from a distance. If your eye can tell the difference between the pure iron and the pure silicon and the pure carbon planets, good for you. My eyes are not quite that good. But again, this is assuming we know the mass and we have the density. And we're not going to get the density for most of the Kepler planets. But hopefully we can still use this technique that I'm going to talk about to get at all of the solid planets that we want to understand. So even in our own solar system, there's actually a diversity of chemical compositions. Only Mercury and the Earth have iron cores that are sufficiently large to generate magnetic fields, which may be important for protecting biospheres from harmful radiation and cosmic rays. The Moon is very iron poor because it formed in a collision where the iron cores of two objects fused into the now Earth, and this formed basically kind of a mantle-like object. And both Earth and Mars are silicate-rich bodies, and of course, Earth is the only one with a little bit of water. So we have a diversity here, but people have postulated about all kinds of compositions, carbon planets, and who knows what the universe makes. This technique will tell us all of it, even if nobody's postulated it yet. So how are we going to get at the composition of solid planets around other stars? Well, we're going to go after the asteroids. And this may come as news to some of you. It was news to me. We actually know more about what the Earth is made of from asteroids in our solar system by the fragments that fall onto the Earth in the form of meteorites. And that's simply because we just can't get down beneath the mantle of the Earth to find out what the core is made. It's totally model dependent in the core. But we can use meteorites to break that degeneracy and get an idea of the composition of the Earth and the terrestrial planets. Okay, and asteroids are important for a variety of reasons. I mentioned they possibly did deliver the bulk of Earth's ocean water and volatiles, which is necessary for life. So how are we going to do this? Well, I said archaeology, future evolution of our sun. We're going to use white dwarfs. Well, for those of you, it's been a while since you had Astronomy 101. Just a reminder, they are the leftover nuclear waste products of sun-like stars and stars a little bit more massive. They're carbon-oxygen cores, essentially one Earth radius, about one solar mass, roughly speaking. And here's just a nice famous one, Series B next to A. And just to remind you that there's no violence when they die. It's just a slow sloughing off of the outer layers, no explosion. I had one referee tell me that everything was changed after the supernova, and I just go, anyway, we've all had bad TAC reports. All right, so White dwarfs are actually quite populous in the solar neighborhood. This is the Recon's data that tells all the different spectral types and their frequency within 10 parsecs. And white dwarfs generally come from stars a little bit more massive than our sun, and roughly a solar mass. But a lot of them come from A and F type stars. And if we look at the number of A and F type stars in the solar neighborhood, white dwarfs vastly outnumber them. So if we're kind of interested in what kind of planetary systems, rocky planetary systems that A and F type stars build, there's actually more remnants than there are actual living stars that represent them. All right, so there's a lot of advantages of looking at white dwarfs. I'm not going to talk about any of those today. I'm going to talk about this phenomenon called metal pollution. And what I'm showing here is a star that was discovered almost 100 years ago by Adrian von Manen. It's a white dwarf. It's the nearest white dwarf to the sun at 4 parsecs. In my opinion, it has the strongest evidence for a planetary system of any at this distance. And what we're looking at here is a spectrum that has only metal lines. It has nothing else. It has a helium atmosphere with no hydrogen whatsoever. And what basically happens in a white dwarf this cool, below about 25,000 Kelvin, is all the metals sink out very rapidly. The surface gravity of a white dwarf is 100,000 times stronger than the Earth, and when you put some heavy elements in it, they just go rapidly to the core. It's always several of orders of magnitude shorter than the lifetime or the evolutionary timescale of the star. So all of these metals in von Manen's star are all pollutants. They all had to come from the outside. There can be nothing primordial left at this stage, and it happened recently. And everything here is iron and magnesium and calcium, very similar to the strong lines in our sun, and no hydrogen. Okay? That's a whole little story about the no hydrogen in some of these stars, but just tells you it's not interstellar medium. All right? It's not companions. That's a whole other talk. I'm sorry I can't give it to you. But what basically our toy model is, which I'm going to substantiate in subsequent slides, is that asteroids have come in. When they get to 1 solar radius, they are tidally shredded because the white dwarf is Earth-size. Say at a regular star, this would just hit the surface. These atmospheres are pure hydrogen or pure helium because of this gravitational settling of the heavy elements. And so the star is actually polluted by the gradual accretion of this asteroid debris. And we know this from a variety of methods, some of which I'll have time to go through. Now, just before you might think, well, wow, that's crazy. Do asteroids really get thrown at white dwarfs? That's a nice story, whatever. Okay. In our solar system, this happens all the time. So in the main asteroid belt, there are these gaps called the Kirkwood gaps, and these are resonances with Jupiter. Jupiter ejects some of them, but a significant fraction of these asteroids go into our sun. So this happens all the time. And I was really excited a couple days ago to see Kate Sue's talk, and she mentioned to us that there are several systems, which probably means it's a very frequent occurrence, where you have an asteroid belt or an inner belt, and you have planets just outside of this. It's exactly the same type of architecture that's going on in our solar system. That's exactly what we need for a planet to just chuck in rocks at the star. So it's likely that the white dwarf phase, that's what's going on. All right, so here's some evidence to back up this picture. We've now measured about 30 debris disks at white dwarfs, almost all of which were either studied or discovered with Spitzer. And the basic takeaway point here is this is an SED, this is the white dwarf, this is the disk. The dust is roughly 1,000 Kelvin. It peaks at about 3 or 4 microns. It's very hot. Sometimes we see a K-band excess, sometimes we don't, and we never see cool dust. We've looked at about 50 of these with MIPS at 24 microns. They're either falling off or they have nothing. And it basically means that this whole white dwarf disk system is about the size of Saturn. It all fits within our sun. So if somebody says white dwarf debris disk, just remember it's a little bit, it's a lot different. Kate Sue has found some evidence for cool dust at some very hot white dwarfs that looks like this. They're more like main sequence debris disks. But all of these stars, these are all metal polluted stars. It's a bit of a different game. All 30 of these have metal pollution. They have this exact same infrared excess, implying that all the material is in 1 solar radius, and that's exactly where large solid bodies will be tidally disrupted. So that's the evidence for backing up this tidal disruption. And we always see the temperature of the dust going up to where we expect it to sublimate, fall into the star, and pollute it. There's a little bit more evidence that tells us exactly where this material is. A small fraction of these are emitting in metallic gas. No hydrogen, no helium emission, only metals like calcium and iron. And basically these are double peaked emission lines. Just Keplerian rotation causes this, and the speed of this rotation is roughly 1,000 kilometers per second, telling us that's exactly where we think it is. There's no models at all. This is just Kepler's law. All right, every one of these that we looked at with Spitzer before IRS died all had this very broad silicate emission feature at 10 microns. This silicate emission feature is not interstellar silicates. It has a broad red wing that is very distinct. It's silicates that are associated with evolved solids in planet formation, such as we see at Beta Pic and Comet Tempel 1. Again, not interstellar silicates. And just for any of you who don't kind of play with this kind of thing, this is the kind of silicate feature we're talking about. These are olivines, and any of you have ever been fortunate to go to the green sand beach in Hawaii, this is basically terrestrial material. All right, so what we do for a living is we look in the infrared to see where the dust is. We get a little bit about the mineralogy, find out what's going on, kind of scratch the surface of the dust. But what we're really after here is for the stuff that falls onto the star and pollutes it, so we use the UV and optical wavelengths to actually get the elements, and we can measure the composition of this disrupted asteroid. And sometimes it's mass. And in this case, we have 150 of these polluted stars from the Sloan Digital Sky Survey, and what I've plotted here is the mass inside their stellar convection zone versus their temperature. X-axis is actually not too important here. We basically have 150 polluted white dwarfs with an average minimum mass in their stellar convection zone that is the same as the asteroid Minerva, which is a 150 kilometer diameter asteroid. It is very large. Some of these are polluted with more metals than the asteroid Vesta, which is actually referred to as a planetary embryo by planetary scientists, even bigger than an asteroid. It's differentiated on its way to becoming a planet when its evolution was truncated. This is the minimum mass that they've eaten because the metals are continually sinking. All right, so we've measured the composition of a few of these things. I'm going to just kind of fly through these last highlights so that I'm running out of time. Basically, one of the most spectacular ones we've measured to date has 15 elements heavier than helium, and its composition broadly mimics a combination of the Earth and the Moon. We were lucky to get some Hubble time. We've looked at 4 very highly polluted white dwarfs. These are ultraviolet spectra, and if we turned off accretion right now, all of these lines except for Lyman alpha would go away in a week. That's how polluted these stars are. All of these are falling under the star at a very rapid rate. Boris Ganzica has a poster on this. He'll be standing at his poster in just a little while. I encourage you to go talk to him in more detail about what the composition is from these we've studied with Hubble. I'll give you a quick broad overview. It's very refractory rich and volatile poor. It is carbon depleted and dominated by iron and magnesium silicates. It is very broadly Earth-like. The material we've seen so far has a diversity that is comparable to the different meteorite classes we see in the solar system, but very basically Earth-like. In some cases, we see evidence for stripping and melting and differentiation, and the total mass that we believe is involved in these processes is at least 10 to the 22, 10 to the 23 grams, big asteroid sizes, and probably more like Pluto mass when you kind of integrate it all together over the lifetime of the disk. All right, a couple more highlights. We found rocky asteroids in the Hyades. There's a nice graphic Space Telescope made for us to announce this. And just look here, these are silicon lines that shouldn't be here. They're polluted with silicon, very low levels of carbon, and if you look at the composition, the silicon to carbon ratio of the rocks that are falling onto these stars, they are at least, these are lower limits, they are at least as rocky as the most primitive rocks in our solar system, the CI chondrites. We don't have carbon abundances, but they are rocky, not icy. All right, so for the Hyades, that basically means that we have large rocky planetesimals in the Hyades, and once you get to the sizes needed to cause this pollution, I think planet formation is inevitable. So even though we're seeing only 50, 100 kilometer asteroids in the Hyades, basically I believe that rocky planet formation has happened at least those 2 stars we found. We have another star that we've identified water with. We published a couple years ago. We've gone back with Hubble and strongly confirms this result, and there are a couple more in the pipeline. So we found some rocky objects, not icy, they're carbon depleted, and they also have evidence for water ice. Lastly, I'll talk about Alma program we had. We had a cycle 0 Alma program, and unfortunately, we studied the prototype polluted white dwarf G2938, which was it was helped to be characterized by people like James Graham. It's the nearest and brightest example, and we only have upper limits at Alma, unfortunately. But what I want to tell everybody in this room is we're getting the composition of these asteroids that are falling onto the white dwarfs. But there has to be a planetesimal belt, and there has to be a planet chucking them in. So if we can detect these planetesimal belts with ALMA, we'll have the composition of these materials, and we'll actually have their orbital location. We'll know where they're formed. And that's about the best, I think, empirical data set that we can give to planet and star and planet formation people. Here's what it's made of. Here's where it's formed. Help us figure out the story behind that. Okay, so I'm going to summarize here. White dwarfs are the endpoint for almost all stars in the Milky Way. And so by studying them, we're essentially studying the remnants of stars like our sun and a little bit more massive. Only a few percent show this infrared excess with Spitzer, but it's simply a sensitivity issue where there's less material. We simply are not as sensitive to see it in the infrared. If you look at the pollution in the star, that happens at least 20% of the time, and our Hubble data is showing it may be as much as 50% of the time. And that means main sequence A and F type stars that are just a little bit more massive than our sun, that means they are constructing terrestrial planets between 20 and 50% of the time. And that's a nice independent estimate from Kepler. We're not detecting planets, but it is informative, I think, in a similar way. And the takeaway point here is these metal-rich, metal-polluted white dwarfs, they indirectly measure the bulk composition of extrasolar rocky planetesimals, which are the building blocks of extrasolar terrestrial planets. And with that, I'd just like to say we're having a conference next year in Cambridge. We're going to talk about this subject and many others, everything related to planet formation across the HR diagram as the name of the conference advertised. I'd like to invite you all to come to Cambridge to discuss how to build planets of all types. Thank you.
Thank you, Jay. And you were very rigorous in keeping to time, so we have plenty. So let's go over here.
Jay, great talk. Did you try, or anyone, has anyone tried to look at one Manen with anything? And do you plan to look at it with Alma?
Look at?
One Manen.
Von Manen star. Well, it's been looked at with Spitzer all the way out to 24 microns and nothing. But like I said, I think it's a sensitivity issue. If you look at the implied accretion rate, it's pretty low.
Well, even if you don't have anything disrupted close in, there would still be this, belt outside. Yeah. So maybe, since it's so close, Alma can maybe do something.
It's definitely on the list for the next round of Alma.
Pretty cool stuff, Jay. I'm blown away by the lack of water you're finding in these things, because currently in our own solar system we're seeing comets fall into the sun with probably more frequency than the asteroids are falling in. And here you've got all the dead stars that have no comets falling in at all. What gives?
Well, it's a good question. I will say stay tuned. I'm not allowed to say anymore. But what I can say is if we use our own solar system as a model, typical large comet mass is 10 to the 18th, 10 to the 19th grams. So a typical asteroid mass, the kinds of things we're seeing are more like 10 to the 22. So those could be just kind of buried in the noise. If we accrete 1,000 of those, then we might see it. But if we accrete 10 for every one of these, I don't know. But I mean, all I can say is so far we're seeing very volatile depleted things, which is why we like the asteroid story. So far, nothing very much comet-like. It may be a mass issue. Not sure. It's a good question.
I'd like just to follow up on that question, because the inner part of the planetary systems, they may be lost, and the outer part may be retained. Okay, during this red giant phase. So you would have thought that the remnants which will strike the white dwarf should be more ice-rich than silicates, and there is a misconnect here.
Well, I don't think that this is an inconsistency. I'm no modeler, but of all the papers that I've read, such as Duncan and Lissauer and several others, I think there's a Ford and Rassio paper, I think it's debatable whether the Earth survives. Venus and Mercury certainly go in our own solar system. Like I said, Earth's debatable, but I've never heard of a model that takes away the asteroid belt in Jupiter and Mars. I think they're all predicted to survive, and so I think that there's a good fraction within the snow line with bodies that should survive the AGB phase.
Do you see any time variability in the lines? And if not, is that interesting?
I thank you for asking the question we always get. It's mandatory. No, but people are looking for it. They've only kind of gotten these kind of 1.5, 2 sigma results. People have debated about it, but it's being searched for, hasn't been confirmed yet.
And one last question. What's the honor of the last question? So, John, go ahead, John.
So maybe I missed this. So, I mean, oxygen is the biggest mass fraction of rocks.
Yes.
So you don't actually see oxygen, or the
Oh,
lines
yes,
just
we do.
not- Okay, all right.
Very
I
much
just
so.
missed that. Sorry.
Very much so, yes. Sorry, 15 minutes only.
Okay, thank you, Jay.